Welcome to another exciting educational video brought to you by Upvision Concepts Academy. If you are yet to subscribe to our channel, please subscribe to our channel to get exciting maths, physics, and chemistry videos. Whether you're preparing for JAMB, WAEC, or GCE exams, these videos are for you. We are here to satisfy your quest to be able to do exams and pass them. Now we are looking at calculus differentiation part 3, and then we'll be looking at logarithmic differentiation and implicit function differentiation. In the last class, we saw the rules for differentiating products, product rules, function of functions, and even quotient rule. Now, the rules of differentiation of a product or a quotient that we have revised before just when you are considering two functions. That is, when you are considering u or y or v being a function of x. So what we saw in those techniques is that we are just seeing two functions, understand? But what if we are giving three functions? That we have three functions, you understand? And for instance, where you have y is equals to u v over w, and all of them are all functions of x. So in this case, we are going to be using logarithmic system to differentiate functions that are more than two. Okay, so the formula or the general expression is to take the ln or logarithm of each of the terms there. So this one now can be expressed as ln y is equals to ln u plus natural log ln is ln or natural log of v minus natural log of w. So this is how it's being expressed. And the differential of this is the same thing as saying 1 over y dy dx is equals to 1 over u du dx plus 1 over v dv dx and minus 1 over w dw dx. So this is how this thing is expressed in general terms, so that you can differentiate it. So mark this formula, note this formula, note it please. It's very, very essential for the differentiation of logarithmic functions where you have the function of x of three composites inside one equation or one expression. So we're going to take an example. Before I go further, to break this thing down, we are only looking for dy dx. So this y, the whole of the function of y will come and multiply this. So finally, this one will become dy dx is equals to y, the whole of function of y, that same function y, then bracket open, 1 over u du dx plus 1 over v dv dx minus, that is for this case, because this is the product of logarithm is plus, and the quotient is now minus 1 over w dw dx. This will change if this one was like this, y is equals to u v w, all function of x. This one will now become plus. So this is what it will look like. So we're going to quickly hop into practical example where we will be solving for using logarithmic differentiation. All right, so logarithmic differentiation, that is the technique. So I'm going to put it on the board like this. Logarithmic differentiation, logarithmic, then differentiation. Okay, so for example, if they say we should differentiate y is equals to x squared sine x over cos 2x. So this is the function on the board. We should differentiate this. Y is equals to x squared sine x over 2x. So I can identify the functions here. Y is equals to this. But there are three functions inside here. This one, x squared is our u, x sine x is our w, our v, and cos 2x is our w. So applying the technique for the logarithmic differentiation, I will now say 1 over y dy dx is equals to 1 over u du dx plus 1 over v dv dx minus 1 over w dw dx. Now, u is equals to x squared, v is equals to sine x, and w is equals to cos 2x. So, I will now come here and say dy dx is equals to, I'll take this y to multiply all this. Y is outside. Remember, y is equals to all of this. But y outside, open bracket, big one. 1 over u is what? U is x squared. 1 over x squared dot du dx. So du dx, that differentiate this one now. If you differentiate x squared, it is 2x. I'm done with this term. Plus 1 over v. What's v? V is sine x. 1 over sine x dot differentiate dv dx, that differentiate sine x, I get cos x, minus 1 over w. W is what? Cos 2x. Differentiate cos 2x. I have minus dot minus sine. Wherever I put sine, these two will come out. Minus 2 sine 2x all over 1. Okay, the same thing like this one here. All right, so I close the big brackets. All right. Remember that this y is this one, so I can just substitute. Dy dx is equals to this y. I shouldn't be seeing y inside here, only x. This y is the whole of this, so I'll just put it there. X squared sine x over cos 2x. I'll leave it there. Understand? This one can reduce. This square, this here will cancel this here. I have 1x up and I have 2x down. 1x will cancel one of the x. So what I have left is 2 upstairs over x downstairs. Plus, this one can resolve as, cos over sine is the same thing as the inverse of tangent. Cos over sine is the same thing as the inverse of tangent. And the inverse of tangent is a cotangent. So I just have it as 1 as cotan x. Please, this one is very easy to resolve. This term here. Let me come here. Cos x over sine x is the same thing as saying 1 over tan x. Why? Because tan x is equals to sine x over cos x. So if this is this, the inverse of this is equal to this. When you inverse this one you're going to get. So it's inverse of tan. That's why I have it. And 1 over tan x is what something as saying cot x. Just study your trig identities very well. You know how they are related. Tan x is equals to sine x over cos x. But we are given that cos x over sine x. You are given cos x over sine x. So if you inverse this, you are going to get the inverse of tan. This and this are the same thing, because from here, if sine x over cos x is tan x, it implies that if you change this one, if you invert this one, you're also inverting this one. That's why you're inverting this one. And the inverse of this one is already cos x. That's why I have cos x here. Then finally, this other one here will resolve as plus because minus is plus 2 outside, sine 2x over cos 2x, close the big brackets. Already this one too is tan 2x. So finally, dy dx is equals to x squared sine x over cos 2x, open big bracket, 2 over x plus cot x. Then this one now plus 2, there's 2 here. Then this one is tan 2x, close bracket. So this is the differential of this. So how did we get here? First of all, we identify that this is a function that has 3 different functions inside. So we're not going to be using product rule or quotient rule because it's more than 2. So we are reverting to a different technique known as the logarithmic logarithmic differentiation. This is only applied when you have more than 2 functions inside a function. So that's the one of the first one that we are working on. So we're going to quickly look at another equation, expression. Okay, so if we are going ahead in the same logarithmic differentiation. So we are giving another example here. It said if y is equals to x raised to the power 4, yes, x raised to the power 4, e3x tan x, find dy dx. Okay, so again, look at this. I have 1, 2, 3 different functions of x inside this expression. So I'm going to apply the logarithm differentiation. It's now saying 1 over y dy dx is equals to 1 over u du dx plus 1 over v dv dx plus 1 over w dw dx. So I have any plus. Why? Because the function is bounded by times operator. The operator bounding these expressions is multiplication. So the logarithm will change to plus. If there were a subtraction here, in this case will change to division, just like we have before. Understand? So if there is a division here, this will change to minus. If there's a division here, change to minus. If it's all multiplication, it changes to plus. So at this point again, I will now say dy dx is equals to y goes here, y open brackets. So I'm going to do all this one. 1 over u, 1 over x raised to the power 4. Dot du dx. Du dx of this is 4x cubed. I'm done with this term. I go to this one, put my hand here. See where my hand is. Okay. 1 over v. 1 over what's v? V is the other of this function. You understand? Dot dv dx, this one. Then I come here, it is 3e3x, that differentiation. Plus, again, this one, 1 over tan x. Then this one is sec square x. Sec square x, close bracket. So we are progressing. So at this point, I will now take this my y. I'll put this expression there. I'll just say dy dx is equals to, then this is what? The whole of this function. X raised to the power 4 e exponential 3x dot tan x. That's the whole of that expression here for y. Then open the big bracket. So I can resolve this one. I have x raised to the power 3 here, h to the power 4. So this one will cancel this one. I will have 1x down here. So it is 4 over x plus this one too we cancel, this and this we cancel, this and this we cancel, I have 3 left, plus now sec square x over tan x. Sec square x over tan x is just the same thing as saying sec square x over tan. I can't resolve this one further. Though you can try, but this is the simplest way it can be. So this is the answer. This is the answer for this. So the whole of the function, then you are adding all the differentials of you you see how it's being done. 1 over that component function, then differentiate that function, plus 1 over that component function, differentiate that function, plus 1 over that component function. What are the component functions? This, and this. So that's the answer for that one. Can we try one more before we go to implicit function? Okay, for the sake of repetition and a sense of, let's try different formats. Logarithmic equation, differentiation. Let's try different formats. This time around, we're going to be having minus. Practice makes perfect. I advise you to practice. So if we have y is equals to exponential 4x over x raised to the power of 3 cos 2x, that's hyperbolic cos 2x. Okay. Now, if you see this one now, if I write the equation 1 over y dy dx, I'm applying logarithmic differentiation pattern because this is 1, 2, 3 is equals to, so this is our u. So 1 over u du dx. Now I'm going to be having minus 1 over v dv dx. Why am I having minus here? Because this is minus. This one here is minus. Division is minus. So, but the same thing goes. If this one is minus, this one is also what? Minus. It's also minus here. Okay, because it's dividing. It's dividing. So I have minus 1 over w dw dx. You see how I apply this? Even if I put minus outside and put plus inside here, these two are doing the plus, but I'm doing the minus outside that I can, go ahead. So at this point, I will just put my dy dx out here, then take this y to this side. That's multiply both sides by y. That's what I've been doing since. So y outside 1 over, okay, let me quickly differentiate now. 1 over u is exponential 1 over exponential 4x dot du dx. Du dx is 4, that's this 4 will come down, e 4x. At this point, I know that you should be familiar with your differentiation. So I'm differentiating as I'm saying in terms. You should go and check out the video for differentiation 1. That's the first principle, the foundation, the differentials, the basic building block for differentiation, standard differentials. So for this one again, I have 1 over v. 1 over v v is what? S cube dot dv dx. dv dx, differentiate x cubed, it is 3x squared. Then minus 1 over w is cos 2x dot dw dx. Differentiate this one now, it is sine 2x. 2 outside, please. 2 outside, please. Okay. So we are progressing. At this point, we can now, I want you to just check, look at this, digest it. We can now simplify. So at this point, I have dy dx is equals to, y is the whole of this. I want to be seeing y inside here. So I have e, or exponential 4x over x cubed cos 2x. Then this one can resolve. This can cancel this. I have 4 left. 4. Then minus. This can cancel this. 1x will remain downstairs here. 3 over x. Then minus 2 can come outside. 2 can come outside. 2 can come outside. That this 2 can come outside here. Then I have this and this will give me tan 2x, hyperbolic tan 2x. So this is the answer for this one. This is quite simple. If you know the principle involved, you're able to get it. All right, so we'll step away from logarithmic differentiation and enter the next one for this video, implicit differentiation or implicit function. When you see implicit function, how do you differentiate them? Implicit function. When you see implicit function, how do you differentiate them? First of all, before you even talk about the definition of implicit function, what are they? What is an implicit function? An implicit function is a function that you cannot separate the y and the x. Okay, I'm just speaking grammar. If for instance, I have y is equals to x squared minus 4x plus 2. This is an explicit function. Explicit function. Explicit in the sense that y is outside. We are outside. Y is outside. It's outside. But if you have a function where x and y are intertwined, they are mixed, such that to separate them will be difficult. Something like this. xy plus sine y is equals to 2. So see this one. This is an implicit function because I cannot separate it. You want to make x y as a formula. How are you going to do it? How? Because this one is inside here. This one is here. You cannot collect like terms for this one. You cannot collect like terms. Already, these are the this y is an angle inside here. So this is an explicit function. They are intertwined. It's difficult for you to separate them. So how do we do implicit? This is implicit inside. Explicit is outside. Explicit is outside. Y is outside. We are outside. Y is outside. You understand? But implicit, y is inside. So how do you do with things like this? For example, if we have, let me give you an example. Let me say, if for instance, let's say we should differentiate. Find the y dx of if x squared plus y squared. Okay, let me take this off so we can have space for it. So we are still talking about implicit function. So if x squared plus y squared minus 2x minus 6y plus 5 is equals to 0. Find dy dx. Find dy dx and the 2y over dx squared when or at x is equals to 3 and x is equals to 2. Sorry, y, not xx. So this is the question. So I agree with me that this is simplicity because everything is inside. You have x and you have y inside, everything is inside, they are mixed. I cannot make y such a formula because by the time I do so, you will see that by the time I group these two, I bring out y outside. Y is still inside somewhere. Y is still inside with minus 6. You understand? So the way to go about differentiating implicit function is to differentiate it term by term. But interestingly, let's see, we'll pay attention of how you deal with the y terms. That's where the skills will be. I can differentiate x. So this one x squared, now I can say 2x. So at this point of your level of your interaction with this course, you know that you can differentiate everything that has to do with x here. But why? How can you do that? So let's go. So you differentiate it term by term. 2x here is, x squared here is 2x. Agree with me? Plus this one too will be 2y. But I have a component of dy dx inside. So when you are differentiating y inside an implicit function, differentiate the y as if it's an x, but attach dy dx to it. I'll take it again. When you're differentiating y inside an implicit function, differentiate it as if it is x. Use the skills for x differentiation. That is, for this one, and the power of y is 2. That power will become the coefficient. At the same instance, that power will drop by 1. That's what happened here. But you will ensure to put the y dx to it always for y terms. Okay, so this one too is just 2. This one the same thing. I'm differentiating this one as 6, sorry, minus 6, you understand? But I will still attach my dy dx plus 0 is equals to 0. So I'm doing differentiation. So I will now collect like terms. I'm collecting like terms anywhere I have dy dx, I group them. The term dy dx. So this is the first term I have as dy dx. So it's 2y dy dx. I group it with 6 dy dx. So it's equals to, I take every constant term to the other side. So 2 will become plus 2, and 2x will become minus 2x. At this point, I can now factorize. Dy dx is common. Dy dx will come outside. Then what's left inside is 2y minus 6 is equals to 2 minus 2x. At this point, again, I can take this under this. That's divide both sides by 2y minus 6. Dy dx is equals to 2 minus 2x over 2y minus 6. So this is the differentiation of this function. But they say we should find the dy dx at x is equals to 2, 3, and y is equals to 2. So at this point, we're going to substitute. We substitute at dy dx is equals to, okay, let me put it this way. We're still on this first differential. We're still on first differential, this first differential, and this first one. So at 3 and 2. See what I did here? This I'm using calculation points to define this. So you know that this first one is x. It's always xy. When you see it like this, it's always xy. So x is what? 3 and y. So at this point where x is 3 and y is 2, what happened to this equation? That's what I'm talking about. So dy dx is equals to put. Where you see x, you put 3. Where you see y, you put 2. Put, substitute. All right. So x is 3 and 2y. Y is 2 minus 6. Okay. So we'll do the maths. Can somebody type the answer in the comment section? Okay. Are we good? So this is what? Okay, this is what? This is 2 minus 6 over 4 minus 6. This is minus 4 and minus 2. Okay. So dy dx at this condition is equals to 2. Okay, so that's for that condition. So for the second condition, I want to take some part off. For the second condition, we know that we need to differentiate this one again. You understand? And this differentiation is going to be like quotient rule. Okay, so at this point, I'm going to take off this side. Okay, let me take off this first side. I will stop at the point where I have my differentials. Okay, let me just take off this one too. So I'm going to differentiate this one again, second time. Second differential, so that I can get this point again. So the 2y over the x squared. So this one now, let me make this one the simplex term. I can factorize on now. 2 outside, 1 minus x. 2 outside, y minus 3. Abi? Cancel. So this is what I'm going to be differentiating. This one. I'm going to be differentiating this one. Okay, so this one now is products, quotient implicit. All right, so in the last video, we said it's bottom the top minus top the bottom by bottom square. Let's go. Bottom, this bottom, I write it. The top is what? Minus 1. Minus top, all right, top. The bottom, this one is 1. If I differentiate this one is 1, remember, but it's implicit. So I'll just put the dy dx over bottom square. This is it now. This is it. So I'm writing this long story. Since I've gotten this one I want to differentiate, let me remove it so I can still leave it. Let me remove it. Let me quickly remove it so that I'll have space to continue. So that's the differential. So this one will multiply. I have minus y. This times this is minus y. This time this is plus 3 minus 1 plus or minus again x dy dx all over, then I will now say this one now. I will still put it like that. Okay, I need to just substitute at this point. Don't need to play too much. Substitute at this point. Substitute at this point. Okay, so substitution. So at x is equals to 3 and y is equals to 2. So y is 2 here, minus 2 plus 3 minus 1 minus x is what? 3. Then dy dx was gotten as 2 in our previous, listen please, gotten as 2. So this is multiplying this one all over, then this is 2 again, 2 minus 3, raised to the power what? 2. This 2 here. At this point, this minus this is 1 plus 1, then this is minus first of all. This and this is what? Minus 2 times 2 minus 4, minus 4. All over minus 1 all squared. This and this is 5 over 1. So at the second differential, dy dx at 3 and 2, the 2y over the x squared is equals to 5. So that's the answer. That's the answer. So that's all for implicit function. So today we looked at we looked at the implicit function we just did and the logarithmic differentiation. So I hope this video has been informative for you. I'd like to thank you for viewing.